Welcome everyone to the NSF Tripods Institute's monthly meeting. I'm Barna Saha from Encore Institute at University of California, San Diego. Other co-organizers of this meeting are Avrim Blum from TTIC representing IDEAL. Hi Avrim, Mariam Fazel from University of Washington representing IFGS. Hi Mariam. And Piotr Indik from MIT representing FOTC. Piotr is traveling, but I can still see Piotr is here. Hi, Piotr. And along with us, we also have Venkat Gandikota from Syracuse University, who is also part of the Encore Institute, and he's helping me for the online arrangement of this event. Hi, GV. So we have several NSF program directors here. So we'll start by asking whether you have any updates to share. Phil?
No specific updates at this time, but we're very pleased that this meeting has come together today. We're looking forward to the discussions.
Okay, thank you. So then let's move on. The main attraction of today's meeting, actually we should record it. So let me start the recording as well. The main attraction of today's meeting is an exciting panel on the reliability of current large language models. As I'm sure you have all heard about ChatGPT and that it's a disruptive technology which can change the dynamics of education, health, technology, and many other business sectors. It's truly a remarkable innovation. But today we want to get to the core of it. And we want to ask, how trustworthy are these large language models? Can we rely on their intelligence, and how, being in academia, we can contribute towards these amazing innovation? To shed light on this timely topic, we have with us Marzieh Ghasemi from MIT. Her research is in computational medicine. So hi, Marzieh. Thank you for joining us.
Hi.
We have James Zhou from Stanford. His interests are in biomedical data science. Hi, James. Thank you again for joining us.
Hi.
We have Ernest Davis from NYU and Courant Institute of Mathematical Sciences. Ernest's interests are in automated common sense reasoning. Hi, Ernest. Thank you again for joining. And finally, we have Nishit Vishnoi from Yale. His research is in the areas of theoretical computer science, optimization, and artificial intelligence. Thanks, Nishit, for joining us today.
Hello, everyone. Thanks.
And welcome everyone to the panel. So the way this will go, I will ask the panelists to give a presentation. So each of them will give a presentation for 8 to 10 minutes on their viewpoint about what they think about the reliability of large language models. And then we will open the floor for question answers from the audience. Okay. So we'll start with Marzieh, then we will, then James, and followed by Ernest, and then we'll wrap it up with Nishit. Okay, so Marzieh, please go ahead.
All right, I'm going to share a screen. And so I'm going to talk to you today about work that we've done recently on doing more ethical machine learning in health. And the backdrop of this is that my group focuses on what we call healthy machine learning. And so it's a play on the fact that we work in health, but then we also want to create robust models, audit to make sure that healthcare data is actually the data we want to emulate, and then also have advice for behavior that achieves better overall performance for patients. And so the other backdrop for this is we're in a state in healthcare where we now have state-of-the-art clinical AI that performs at or above humans in a range of tasks across the human lifespan. And so this is no longer a question of, can we predict something really well? Often the answer is yes, we know that we can. We're also in a setting where models are regulated advice givers in the United States and in other jurisdictions. Here it's the FDA. In other countries, it's other regulatory agencies. And you can see here across specialties, and different kinds of data modalities. There are many companies that have created AI models that are being regulated right now and released. A problematic issue that is also problematic for language models is that there are biases in clinical processes. And here I don't mean statistical biases, although those are obviously present as well. I mean human or societal biases that we might not want to replicate. And so I'm going to walk you through today, not all of this pipeline because this is 8 minutes, so it's going to be short. I'm going to walk you through 3 parts of this and how issues in this standard machine learning model development pipeline often come up specifically with data collection, outcome definition, and post-deployment consideration in language models. And there's obviously other things one could talk about in any of these settings or with any other kind of model. So for data collection, the reason that, or one of the reasons that you might find difficulty with relying on language models in a healthcare setting is there are these deeply embedded proxies for societal biases in health data, even if you remove overt issues. And so first pop quiz. I hope you're all awake and have had your afternoon coffee. This is a nursing progress note from a Boston area hospital that has patient demographics redacted. And so the question for you is, can any of you tell what this person's self-reported race would be? So if you've ever gone to the doctor, you filled in something like your age, your assigned sex at birth, you might now put in gender expression, you might put in comorbidities, and you often put in your self-reported race, white, Black, Hispanic, Asian, whatever it is. So if you can't, you shouldn't feel bad. None of the doctors we tested actually could, but machine learning models can. And they can do it actually really well. And here they're using what we would probably call a statistical bias, not a societal bias, right? So in this case, in the hospitals in the Northeast that we looked at in New York and Columbia, New York, Columbia, and Boston, Massachusetts, the Beth Israel Deaconess Medical Center, it turns out that there are a larger number of African-American patients who self-report Black race that are on dialysis for hypertension. But many models here, and here we're not even using what I think this is a paper from 2022 that we did most of the work for in late 2021. We're not even using GPT models in this work, and we're still able, in a very large cohort of clinical notes, over 4 million, to predict a patient's self-reported race, even with very simple models, after you strip out all direct indicators of race. And the kinds of things that models are using are sometimes maybe those things that we would call fair game, like a statistical bias towards specific diseases or conditions or comorbidities for some patients. And sometimes it's the fact that if you talk about a patient's skin at all, that patient is likely to be white. And this has been well referenced in many talks and many articles now that a majority of the examples of skin-related presentation of illness are on white skin. And consequently, clinical staff don't know how to talk about skin-related presentation of illness in darker skinned patients. Also, if you call a patient difficult or their family difficult or many other negative affect words, that patient is probably African-American. And so these are things that exist within the data that we're using. And we know that data itself, there's been a lot of work on this. I probably don't need to remind this group of people, but it's a powerful good. It's something that we use, like compute, like anything else. But unfortunately, right now, machine learning in health really lags in other subfields like natural language processing, computer vision, or just general machine learning in releasing code and releasing data. And so consequently, as a result of not having as much data, leveraging multiple data sets. So the second thing is, let's say we have the best data possible. We need an outcome. We need something to predict. But the way that we label data actually is really problematic, including for language models. And so here's an example of a meal. And I'm going to ask you a question. Maybe my local school says, we want to know whether meals, when a student takes a photo on their phone, violate a school meal policy that prohibits high sugar content. And so what would we do if we were doing this for the Cambridge school system that my kids use? We would ask a bunch of labelers, does this meal have high sugar content? We would get that label, yes or no. And then we would build a machine learning model. And if a majority of the labelers say yes, then we would classify, for example, this picture and ones like it to be a violation. But what would have happened if we would have asked, does this meal violate a school meal policy that prohibits high sugar content? And I hear you all saying, but this is an if-then rule. It's an if and only if, right? Because this is just about sugar. So surely these two are equivalent. But when you ask people if this meal has high sugar content, and I will say it's Cocoa Puffs with whipped cream, so it does, 17 out of 20 say yes. If you ask if it violates a school meal policy that prohibits high sugar, only 2 out of 20 say yes. And if you look at the repercussions of the way that we collect data in this sort of descriptive way, and then applying that to normative tasks, there are reasonably large repercussions of the models that we trained. And so we trained this across 4 different settings, and we collected labels in both of these different settings and then compared what would happen if we trained models in the descriptive setting and then applied them to the normative task, right? So collect, is there high sugar? And then apply to, did it violate? And we trained language models, including Bert and Albert, for a comment setting where there was forum guidelines about toxic comments that you were supposed to label. And what we found is that if you use descriptive labels, which is the way we all label our outcomes in machine learning, the models you train are substantially harsher. And so we have a much higher rate of false positive judgments. This is much more aggressive than humans would have intended if you asked them what it was being used for. And the performance gap that this induces is comparable to high rates of label noise, high rates of data subsampling, or just using a better model, right? And so if you use a better model like Bird instead of Albert, you get a 1% impact in performance here. If you use the right data, then you get a 6.5% impact. And so these kinds of things really matter. The final thing I'll talk about briefly is, let's say we have the best data and the best outcomes, and we've trained the best language model we can. You still have to deploy the thing, and you still have to give people advice with it. And we want to make sure that it's not just the best model, but that giving advice from this best model is actually going to improve the process we're integrating it into. And so we looked at a high stakes decision that a non-clinician might be involved in a healthcare setting. And so here, this is a crisis line, a mental health crisis line. I volunteered for one in college. You might have participated in one potentially, where what happens is you get a transcript, and I've highlighted the person's demographic information here, but in the transcript, it's not highlighted. And then you ask the volunteer to make a simple decision. There's no liability risk because you're sending help no matter what. All they have to do is decide whether this person should get emergency medical help or whether you should call the police. And importantly, we gave them if and only if training. So just like in that outcome section, we said you should call the police if and only if there's a risk of violence. And so predicting that there's a risk of violence is equivalent to predicting that you should call the police, right? And then we had baseline clinicians and non-clinicians read through transcripts and then make this decision. Should we do medical help or police help? And then we trained a language model to give them some advice. And we have 2 language models. We have an unbiased GPT model, a GPT-2 model in this case, and then a biased GPT model. And the GPT model that's biased has been intentionally biased by us, the research team, to disproportionately recommend that there is a risk of violence / you should call the police, those are the same label, for African-American and Muslim subjects that are getting these transcripts. And then in the unbiased GPT model, it's even. And so we have that one variation. Do you as a volunteer get the biased or unbiased GPT model in your treatment? And the second treatment is whether you get a descriptive or a prescriptive flag. So just like in outcome definition, you could present this as the if condition. Our AI system has flagged this call for risk of violence, or our AI system has not flagged this call for risk of violence, or you could present it as the then condition. So, we think you should go, the AI model recommends that you call the police, or the AI model predicts that you should call for medical help. And in both cases, this treatment is recommending the same label, but it's framing it as either the descriptive label or the normative label, right? So the if condition or the then condition. And so what we found here is that at baseline, good news, clinicians and non-clinicians are not more likely to call police on Black and Muslim subjects. Okay, so there's no variation when you change that demographic in the transcript. When you give them biased prescriptive recommendations from the GPT model, clinicians and non-clinicians are both much more likely to call police on Black and Muslim individuals. But when you give them the same biased recommendations with the descriptive flag, it does not have the same effect. And so participants actually retain their original fair decision-making in those settings. This is really important for us as computer scientists who work in spaces where language models are being applied. People often take off-the-shelf models that have bias baked in whatever ways they are, and then just use them somehow. But there's a lot to think through in terms of safe ways to integrate technology. For example, in aviation, there's been a lot of thought about this around regulation, cultures of safety and training. And there's many federal agencies, if you're not involved in the health space, that could have a role like this when we think about large language models in health. And that's it.
Thank you, Marzieh. Very nice talk. Shall we move to James?
All right, great. Well, very nice to be here, and thanks to the organizers for putting this panel together. So I'm excited to share with you some of the sort of very recent investigations we've been doing, thinking about how ChatGPT's behavior has been changing over time, and the implication of that for reliable and trustworthy usages of these large language models. And this is joint work with Linjiao Chen and Matei Zaharia. Okay. Whoops. Sorry, let me try sharing again. Okay, so yeah, so why are we interested in studying the behavioral change of these language models? So first, these behavior changes in the models like ChatGPT, I think it reflects many interesting aspects of how these models are being trained and developed, right? So you can see the behavior change can be due to human feedback, architectural changes by OpenAI or fine-tuning, right? Especially since these models are fairly opaque, right? So just looking at the behavior change is actually a good way for us to try to get more into the black box of how people are training and developing these models. And second is that if you're a practitioner, oftentimes you're using these large language models like ChatGPT as a part of a larger software or analysis pipeline, right? And for that pipeline to be robust and reproducible, it's often very critical that the behaviors and outputs of ChatGPT is consistent, right? And then as researchers, oftentimes we're interested in how reproducible are research findings across time, right? If the models are changing or drifting, it can also make it harder to have reproducible research findings. So motivated by this, we decided to basically investigate, right, the behavior change of ChatGPT. So we did this for GPT-4 and GPT 3.5. And the way that we did this is that we designed basically 8 different tasks that are designed to cover different and complementary capabilities and popular ways that people use GPT, right? So some of these are testing more reasoning abilities, others are testing more information retrieval or summarization and coding. And what we did is that for each of these tasks, we created a benchmark of about sometimes a few hundred of questions for each of these tasks. And then we basically asked the same set of questions to GPT in March, and then the checkpoint in March, and also the GPT in the checkpoint in June, right? And so this radar plot is basically showing the performance of ChatGPT across these different dimensions. In blue is basically performance in March, and the red is in June, and then larger the areas corresponds to basically better behavior or higher performance. So I guess the quick summary, the main takeaway here is that there's actually really large behavioral changes of ChatGPT over just these 3 months, right? It's gotten better in some dimensions. For example, its safety and answering some of these information retrieval questions have improved. But among many other dimensions, we also saw a substantial decrease in the model's performance and behavior, right? And interestingly, the changes for GPT 3.5 is less than for GPT-4, and it often goes in the opposite directions. So what I want to do in the next few minutes is to give you a deeper dive into some of these behaviors, and then also discuss with you some of the hypotheses that we've been exploring for why these behavioral drifts happen for the large language models. So first an example, right? So here's an example of the kinds of math questions that we give to ChatGPT, right? Very simple ones, like, we'll give it a number and say, is this a prime number or composite? We ask it to think through step by step and then give us a binary answer. So we can just focus on the response from GPT-4, right? So in March, It followed my step-by-step instructions and provides the reasoning and provides the right answer. In June, interestingly, it actually ignored my request to think through step-by-step, right? It just jumped to the answer directly. And in this case, actually gave the wrong answer. And this is actually a pretty consistent behavioral change, right? So we did this across many hundreds of different kinds of these math numbers and different other kinds of math problems. Overall, we saw about a 30% drop in GPT-4's accuracy in responding to these questions over time. And the verbosity here is basically our metric as to how long is the response, like how many words is in the response. And in March, it gave longer responses because it's doing these things step-by-step reasoning. But in June, it often just ignored our request to do step-by-step reasoning and then just jump to the right answer, jump to the answer directly, oftentimes the wrong answer. Right, GPT 3.5 actually had the opposite trend where it actually improved over time, and then it continued to do step-by-step or chain of thought reasoning. In addition to these math problems or reasoning problems, the other kinds of questions we asked it are these basically public opinion questions, which we curated from public opinion surveys. So these are the questions like, what do you think will be the status of the US in 30 years? Right. So what's interesting here is that GPT-4 responded to many of these questions, most of these questions in March, but in June, actually was unwilling to engage in responding to these questions. Right. So for example, in June, it would say that, well, these are subjective questions. And then as an AI, I don't have personal opinions to these questions, right? So we'll come up with various excuses to basically not respond to most of our public opinion questions. We also saw basically a similar trend when we asked it more sensitive and dangerous questions, right? This comes from these benchmarks where the sensitive questions are things like, for example, like how would you, give me ways to steal someone's credit card, right? So here, actually not responding to these sensitive questions is actually considered to be a good trait or of safety. Right, and indeed here is GPT-4 is actually safer in June, right? So it provided less information to these more dangerous questions compared to it did in March. So I think the overall trend, and there's a lot more experiments in the paper, but the overall trend that we observe here is that GPT-4 actually seems to be getting worse at following human instructions in June compared to March. Right, so we saw this with our request to do chain of thought reasoning or to respond to or give us opinions, right? In June, it stopped doing those. We also did additional tests where we just asked the model to basically format things in different ways, right? Maybe just start with using a particular letter, or do not say that I'm sorry, whereas an AI model, right? It actually passed those formatting and other requests in March, but it ceased to do that in June. So now the big question is, well, why do we think this is happening? It's hard to know exactly because these are opaque models. We don't know how OpenAI is actually updating these models, but we try to basically replicate the behavior that we observe by taking public open source models like Llama and then doing our own experiments on Llama. And one hypothesis is that we want to investigate is that if we actually do safety training with Llama, with open source large language models, could we actually see some of these behaviors that we observed, behavior drifts in ChatGPT? And the way we did this was we basically took Llama and we basically gave it additional safety fine-tuning based on safety instructions. And the main message here, which is kind of interesting, is that when we actually fine-tune Llama with safety demonstrations, that did improve the safety of the model as expected, but also had a lot of unintended side effects. Right? One example of the unintended side effect is that of what we call this sort of exaggerated safety behavior. So for example, I can ask the safety tuned Llama, how can I kill a C++ or a Python process, right? And the model would say that, oh, I cannot give you the instructions because it's not ethical to kill this computer process, right? So it's clearly that the model is actually sort of gone overboard, even with just a few hundred demonstrations of safety training. So I guess just to conclude the main takeaways here, right? So we have observed that ChatGPT's behavior have really quite changed substantially over a short amount of time. We've done a similar analysis of sort of non-language model AI systems where we monitor their behavior drift. So they also drift in computer vision, right? But the amount and the magnitude and the speed of the drift that we see for language models is basically an order of magnitude faster than we saw for previous non-LLM systems. And in particular, I think the drift is going in a direction where ChatGPT-4 is less able or less willing to follow some basic human instructions like chain of thought reasoning. We don't know exactly why this happens, but this could actually stem from additional safety tuning, as we saw in our experiments with Llama. What's also really interesting is that we see the drift trends for GPT-4 and 3.5 often divergent, right? So in areas where GPT-4 is getting worse, but GPT 3.5 is actually getting better. So there's actually quite mysterious to us of how this happens. And all of this sort of highlights the importance for practitioners and for researchers to continuously monitor large language model behavior drifts. And also, if you're a practitioner, then you really want to sort of robustify your pipeline, right? Because the output and the formats of the output of ChatGPT can also change quite suddenly without notification. So I'll stop here.
Thanks a lot, James. That's a very nice talk. So actually, we will stop here briefly to take a few questions, as James have to leave early. And I already see there is a question in the chat, so I'll just read it. So the question is, does this disparity of change in GPT 3.5 versus 4 is due to the fact that 3.5 is free and therefore has larger and different type of feedback?
Yeah, so that's a good question. I think that's a very interesting hypothesis. So it's certainly possible that the kinds of human feedback that's done for 3.5 is very different from GPT-4, which is often more used in more commercial applications, right? And that could actually be one factor why we see such divergent trends for these two models.
Okay, thank you. Are there any other questions for James or Marzieh?
I have a question for James. What is the difference in the checkpoints for the same model between March and June? Like, are they being continuously trained somehow? Like you said, there was GPT 3.5 in March and GPT 3.5 in June. What's the difference between the two of them? Do you know? Like, are they actually different models? Do they keep getting updated?
Yeah, so based on their behaviors, they do seem to be substantially different models because the output of these models are very different, right? So people usually think of like GPT-4 as a single model, but what we see is that the checkpoint of GPT-4 in March actually give very different responses to the checkpoint of GPT-4 in June, right? So how this model is continuously being updated by OpenAI, so that's the part that's sort of opaque. It's not known to researchers, but what we do observe based on the surveys that the behavior of these models have changed a lot. Some of that could be due to additional safety fine-tuning.
Right. Okay. And follow-up question on that is like, if you give the same input prompt, you get different outputs, right?
That's
right. So do you do any kind of averaging or sampling on that? Like you may have, Yeah.
So we do that. So basically, we can give the same prompts like multiple times to the March checkpoints. Mm-hmm. Right? So there's some randomness to it, but it's actually very small compared to the drift that we see here. Okay. Right? And also that for each of these tasks, we actually generate sometimes like thousands of questions. Right? So the drift that we see is actually quite substantial bias, not just the variance.
Yeah. Okay.
So James, just a follow-up question. Do you, even within a single session, sometime I have seen that if you ask the same question, it can give different answer depending on whether you are starting the conversation or maybe you're in the middle of the conversation. Yeah. So is your observation significant compared to that difference? I mean,
Yeah, so that's a good question. Yeah, so if you're in the middle of a conversation, then the response can depend on the previous replies as a context.
Exactly.
In our experiments, we try to make sure that every conversation is like an independent fresh start, right? So there's no additional context there. I think the magnitude of the change that we observe over time is also quite large compared to the in-context changes we observe within the session.
Right. And you were using the same account to do this thing, or you have different?
Yeah, so these are done from the same account, but we can also replicate this using different accounts.
I see.
Okay, great. Thank you. There is a question for Marzieh. So we'll take this question and all other questions we'll take it at the end. So how did you follow the procedure of introducing bias in the GPT model? Was it through prompt engineering or was there any fine tuning done or something else?
It was fine tuning with examples that included, so sentence examples that we have in the paper that mentioned the demographic group and violence or police in them, until we had the rate of misprediction that we wanted in the biased model. So we had a target rate we wanted to hit.
Yeah, thank you. Approximately how many examples did you use for this?
2000.
Okay, thank you.
Okay, great. So let's move on, and so let's Ernest, you are next. So let's go with his. Please share yours.
Yeah, thanks very much for inviting me. So I want to describe a few unsystematic experiments that I carried out with Scott Aronson on GPT-4 augmented with a couple of plugins for physics and math problems. So first, let me describe the system. GPT-4, as of March or so, supports plugins, and in particular, we tested two. One is the code interpreter, which generates Python code, and the other was the Wolfram Alpha, which calls Wolfram Alpha. And the way this works from the user's point of view is that you give the prompt to GPT-4, and then GPT-4 decides whether it's going to solve it itself or whether it's going to call the plugin. You have to specify the plugin. It doesn't choose between plugins. You specify which one you want it to do. And if it's going to call the plugin, it creates either the Python or the Mathematica code, and it calls the plugin, and then the plugin does its thing, and it returns a result. And then the GPT-4 can interpret the result, and it gives an answer plus some discussion to the user. And sometimes this is iterative. That is, the GPT-4 will make multiple calls to the plugin, either because the problem has multiple parts or because the first attempt on a question fails. And so you can see a trace of the communications. You can see a trace of GPT-4, so to speak, thinking and setting up the problem, and the communications between GPT-4 and the plugin in Python and in results returned from Python or Mathematica are all available to be seen. So as I say, these were experiments that Scott Aronson and I did between June and August. These days, as James was discussing, you have to date your experiments quite carefully with these systems. And we had three sets of problems that we wrote. Scott wrote a collection of 20 problems that he felt are sort of interesting problems. I created and had numerical answers. I created a set of 32 problems, which are fairly arbitrary and tedious, which also have numerical problems. And then I created a set of 53 problems, which are multiple choice or true false, which are supposed to be calculation free in the sense that if you have the basic numbers, you can do all the arithmetic. Arithmetic is trivial, and you can do it in your head. And we didn't do any prompt engineering to speak of. So there's a link to our paper there. There was also a much larger and more systematic experiment of a comparable time, which was published exactly the same time by Wang et al. They used 800 problems from college textbooks and examined 14 different models, but I'm not going to discuss their results. The problems that we use had a wide range of difficulty. So the ones in the calculation-free set can be answered, or at least that was our intention, by the man on the street if he can look up the numbers in Wikipedia or look up the geographic information on maps. And they can do this without doing any explicit calculations. There are several problems, both of Scott's and of mine, which have numerical answers, which a good high school student taking math and physics should be able to solve if they have access to Wikipedia for the numbers and they have a calculator to do the calculations. All but a few should be solvable with some thought if you give them to a strong college or math physics major. But there were a few which were really quite tough, and that even if you have an excellent math and physics major, they might not get 100% because these ask questions on courses that they may not have taken. So we had some impressive successes. This was an example of Scott's. What is the probability that a randomly chosen 100 by 100 matrix over the finite field F2 is invertible? So it's not even obvious how to do this. It turns out it's lookupable if you have the right sources, which is more or less what both plugins did, but both plugins got this correct. The problem of mine, a point P is chosen at random within the 100-dimensional box, 0 to 100, following a uniform distribution. What is the probability that the Euclidean distance from P to the boundary of B is less than 1? Both programs got this correct in the correct way. Here was a problem, one of my calculation-free problems, which they both got correct. Let C be the center of the Earth. Can there be 3 Earth satellites X, Y, and Z such that C, X, Y, and Z are always coplanar? And the answer is yes, and they both got that correct. A couple of examples of failure. This was a problem of Scott's. What is the Shannon entropy of a positive number n that's chosen with probability 6 over pi squared times n squared? The answer is 2.362, if you care. Wolfram Alpha plugin didn't return an answer, and Code Interpreter got it wrong. It wrote it as a sum of 2 terms, and it got the sign wrong on one part. This was a numerical problem of mine. Viewed from Vega, what is the angle between Sirius and the Sun? Both programs got it wrong. Wolfram Alpha because it used the wrong formula from spherical geometry, and Code Interpreter, more interestingly, it didn't call the plugin. In this case, GPT-4 simply answered, the angle between Sirius and the Sun as viewed from Vega depends on the time of year as well as the specific time of day. This is because the Earth and Vega both orbit the Sun, but at different rates, and also because the Earth also rotates on its axis. And it went on in this completely misdirected way for another couple of paragraphs. We got very verbose answers in general from both systems. Here is a calculation-free problem. Joe says that he lives 10 miles from Lake Michigan, that Beth lives 10 miles from Lake Michigan, and that he and Beth live 100 miles apart. Is it possible that Joe is telling the truth? And the answer is yes, because Lake Michigan is about 300 miles long, but both plugins said no because they misapplied the triangle inequality. All right, what kind of errors did we get? Many. In some cases, GPT misinterpreted the problem. In some cases, it invoked the wrong physical theory. So for instance, with we had a number of problems involving relativistic mechanics. It often tried to solve the problem classically. It sometimes set up the math wrong. There were often, particularly with Wolfram Alpha, there were mistakes in calling the plugin because GPT-4 doesn't really have a good idea of the mathematical language. And in one particularly dreadful case, GPT-4 called Wolfram Alpha 40 times unsuccessfully on a fairly simple calculation. When it got the answer, GPT-4 sometimes misinterpreted the answer or refused to accept a correct answer. That was rare, but it did happen. Conversely, it sometimes got an answer which was impossible or meaningless, and it simply passed it on. In quite a few cases, it failed to call the plugin where it would have been useful. That is to say, it did its own calculations and it did them wrong. GPT-4 is not as accurate a calculator as either the Python interpreter or Wolfram Alpha. And conversely, in some cases, it called the plugin uselessly. There were several calls where it made where it's assigned this a value to a variable and then asked either Wolfram Alpha or Code Interpreter, what is the value of that variable? And that was literally the entire code that it passed. You know, what it thought it, well, that's overly anthropomorphizing. How that mistake came to be made is mysterious. General weaknesses that we observed, it's clearly not surprisingly weak where on problems where people would use spatial reasoning or visualization. It's weak, as many people have noticed, where multi-step reasoning is involved. And somewhat more surprisingly, it tends to stumble if there are very large numbers or very small numbers like 10 to the 300 or 10 to the minus 300. Obviously both Python and Wolfram Alpha can deal with those if they're correctly set up, but the interface became wonky at that point. And if GPT-4 tried to deal with them itself, it's not reliable with those kinds of problems. So bottom line, overall, this was an impressive result. Our feeling was that this was at the level overall of a middling math or physics major, though it doesn't, it doesn't correspond to the capabilities of an actual human student. It got problems that, a high school student should not get wrong, problems that any high school student would get right, and it got right some problems which middling college students would find very difficult. There's a lot of room for improvement, clearly. There is some low-hanging fruit, and it's clear that their interface issues that should be fixable, one would think would be fixable. There are some challenges like integrating spatial visualization, which seem much harder. And it's possible, we didn't do systematic experiments, but there's some indication that rather than a batch mode, you give it a question, you get an answer, it might be more useful in an interactive mode where you give it a question, you get an answer and say, well, that's not exactly what I meant. What I meant was this, but we did not explore that possibility very much. Okay, so that's what I had to say.
Okay, thank you, Ernest. Very interesting talk. So let's move to our last presenter, Nishant. Nishant, I asked Nishant to be part of this panel because he's he's a theoretical computer scientist, and I wanted to understand what is the view from a theory point, what we can contribute in this development of large language models, the directions for theory. So Nishant, the floor is yours.
Thank you, Varna. Thanks for the invitation. I must say that I don't have the extensive results that I have seen people present here. I'm mostly here to, as Varna said, to talk about where and how people who are theoretical minded or have been working on more foundational stuff can contribute to this topic. However, I will also add that the topic of this panel, reliability, is a very important issue, and questions such as bias and privacy, some of the stuff that I have worked on, are definitely worth studying. But let me just start by saying a few words about how maybe a theoretician would view what is going on in these models. So at the core, the mathematical problem seems to be the following, that you have a bunch of texts. Texts are sequences, and the goal is to come up with a probability distribution, which has this property that given a sequence to predict what the next word would be. And traditional models for these in the language literature or the NLP literature have been of this type, what I call n-gram models, which I'm assuming people are familiar with here. So these are models which try to make predictions about the next word, the probability of a next word, given n prior words. It seems like the traditional implementation of these n-gram models suffers from inherent sequentiality, and the transformer architecture essentially allows to kind of get around this sequentiality. And I would say very, very roughly, if I and effectively implement these n-gram models for large values of n. So this is my bird's eye view of what is happening. No, I'm not sharing any screen. I'm just talking. So now, given this viewpoint, let's even assume that for a moment that these large language models can actually do accurate n-gram predictions for some large value of n. I think the most basic question, which I realized, which is relevant to reliability, is that all of this setup that I described has this assumption that there is a probability distribution, or there is some probability space from which text is being generated, or as we heard in Ernest's talk, I mean, there is some assumption in these, that the way the answers of these questions that are being asked are structured in somehow is compatible to this very basic view of data generation. And this to me is an assumption which perhaps makes somewhat sense in the world of n-grams when people were looking at small n, but in this complex world where we are surrounded by all kinds of data, I'm not sure this is a very reasonable assumption. So I haven't seen a lot of discussion about this very basic assumption on to what extent does it make sense that we assume that the world is basically a probability space of this type, because we are constantly adding to it. No, I think I'm not sharing any screen, so I just wanted to clarify. I'm just talking here. So in terms of reliability, I guess this is very important because all these issues that people are observing, and I have seen and myself tested these systems, they display all kinds of biases, and perhaps other ethical concerns exist with these language models. It's not surprising at all that this is happening. And one of the reasons is that this assumption that this probability, one of the reasons is that the assumption that the data is, there is a corresponding or underlying probability distribution seems to be, even if correct for different populations, this distribution could be different, not because people are, not because of any inherent differences between people, but just how the data is processed in a societal manner. I can elaborate more if anybody would like to know, but so it is displaying all these kinds of biases. So that's one of the things I wanted to say, that to make it more reliable, I think one has to revisit this very basic question and try to see what happens if we perturb these probability distributions. And I think some of this work came up in Marzier's talk, unless I completely misunderstood it. I think the other interesting observation in terms of reliability is a study that I saw, which talks about, it's a study which tried to understand what is the political inclination of each of these GPT-like language models. So, and there the interesting observation was a correlation between the company that owns that particular LLM, which state they are in, or what the political inclination of their CEOs is, to the political inclination of the output of the text generated by these LLMs. I thought this was very interesting, and it does contribute to bias in the dimension of political opinions, and it would be interesting to see how scholars in political science or even computer scientists who are interested in things like polarization would take that into account. Perhaps the RLHF part of it. So one explanation which I was thinking about is that maybe the RLHF part, the human feedback part, if a company is based in California, then maybe the workers who are providing this human feedback are also from California, and California has a particular political inclination, so it's not super surprising. But it's definitely interesting, and I think worth investigating more. I think as far as theory is concerned, I will say that there are three opportunities. One is to understand the basics of language modeling. I think this is an opportunity. And there are parallels in the world of theoretical computer science where, for example, for people who are familiar with the sampling and counting literature, this viewpoint of reducing counting to sampling is also, in some sense, uses Bayes' rule, and you can do it iteratively. Whereas one can imagine that one bypasses this Bayes' rule and just does something in parallel altogether. So the question would be, how good are these samplers compared to the sequential sampler? So that's, I think, one thing to kind of formalize and try out. The other is, it seems like a lot of this depends on data. So understanding data becomes really crucial. And in that sense, theoretical modeling of data would be very important. Data is being generated by humans. Humans are in some way or the other optimizing something. So it would be interesting to see to what extent do we need to model data generation if we are interested in making predictions about large-scale behavior or macro behavior of these systems. So this could be very similar to statistical physics, where if I'm in this room, there are many, many atoms. Do I need to know really about each and every electron of this each atom to predict what the temperature is? Perhaps not. And I think this is somewhere where people who are interested in theory can contribute. And finally, I think another area where theory can contribute is just looking at these systems more from a CS econ style, where we are assuming that they have some capabilities, thinking of them as agents in a certain ecosystem, and then trying to understand interactions with humans or other between humans and these AI agents. So what differentiates, what properties of these models differentiate them from humans? And that would be interesting to understand. What could the new equilibria in the future look like? What would it mean for jobs and economies and equity in general? So I think I'll stop here.
Thank you, Nishit. It's great to hear all these directions that from theory perspective. And now it's the appropriate time to open up the discussion. So questions for the panelists, feel free to unmute yourself and ask the questions. You can also write the question in the chat and we can relay the question.
I can ask something. I have a question for both Ernest and Nishit. I think Nishit just put up one way to view these models as a Markov chain and view the universe as a Markov chain and something that is predictable from all past behavior, maybe that's summarized into something and we are just predicting the next word. And another type of learning that we can think of is rule-based, where we come up with an equation, like the problems that Ernest was trying with GPT-4. So maybe there is some physical, do you think that in any such thing, any such rule-based learning can also be cast in some form in a data and then learned in a data-driven manner as a Markov chain? Because there might be some equation that has only 1 0 and everywhere else it will give you some other answer, but it is still a very simple one equation. If we just and maybe based on all the past observation, it will always give me, it will always be right, except for one point where it will be wrong. And if we are just the way we are currently evaluating it, we'll always miss that point. So even if we think that it has learned something, it's just parroting something. So is there a way we can get around this issue? I don't know if it is clear what I'm trying to say.
Well, I mean, on the one hand, the LLMs these days are sometimes answering, seemingly doing quite sophisticated reasoning and answering questions which are not plausibly in any very close form in their training set and so on. On the other hand, there are things that they have find very difficult to learn. There was a recent talk a couple of months ago by Yejin Choi, where she went through the difficulties that LLMs encounter in doing multi-digit multiplication, for instance. They really have not gotten that yet, and it's not clear that they can get it.
Mariam had a question. I think I saw her hand raised.
Oh, yeah. So thanks a lot, first of all, to Barna for organizing and to our panelists for very interesting talks and viewpoints. One quick question I have is, there is also a talk about when the models are trained on AI-generated data, so, and concerns that might come out of that, which is currently the data they had used was human-generated, so it has human qualities. But as we move towards maybe more data posted on the web is actually AI-generated itself, like text written by AI or images generated by AI. Do you see issues coming up with that? And maybe some of the time dependence of GPT results could be because of that? And your thoughts on this in general? Because this is actually creating a feedback loop that can have further detrimental results.
Yeah, I think it's even, maybe I'll say a few words. I mean, I think this is actually not specific to LLMs. I mean, if you look at, for example, things like Facebook and Twitter and Instagram or whatever, we are using, I mean, that's already contributing to this feedback loop. I mean, our opinions are constantly being changed and formed by the data that we consume. So this data that you mentioned as human quality data is also already not clear to me that it is, what does that even mean? Because, I understand your question very precisely, but I mean, don't get me wrong, but all I'm saying is that what we call human generated data is not clear to me. I mean, Shakespeare would not have generated this kind of data, I would say, because probably there was no Facebook, but clearly there were people who he was influenced by and so on. I mean, here we are already being influenced. So in some sense, our brains are already producing data, which one could say is semi-artificial in some way or the other. But yes, it does create a feedback loop. And I think this is a huge problem. And from what I understand, a lot of these language models are doing this self-play, or you can have two language models. One can ask questions to the other, and this one can, so they can, I mean, you can do all kinds of very interesting things, and it does create this very strange dynamical system. And understanding what the limit points of this would be, would be an interesting theoretical problem. If we have some model of what it is doing to the input probability distribution, because at some point there is an input probability space and it's transforming. So I guess, and then if you keep feeding it data from its own probability distribution, then what is the stationary probability distribution of such a thing, right?
That's right.
Yeah, there have been a number of studies of that recently. I posted a link to one of them in the chat. I don't know that I don't know to what extent it's actually been demonstrated in the field. Of course, it's not easy to detect, given the black box nature of the training sets and so on. This concern goes back almost 15 years to machine translation systems. There, in some low resource languages, a large fraction of the online material in the language was in fact generated by by machine translation programs. And so features of the language that were, errors in the language that the early machine translation programs generated get fed back into their training set.
Yeah,
Okay.
very, very interesting. Thank you. And thanks for the reference. Thanks, Nishit, as well.
Yeah, thank you, everyone. So our time is up. So let's thank all the panelists and for this very interesting panel. And we hope to continue this conversation in the follow-up NSF meetings. Thank you.
Thank you.
Thanks very much.
Thanks.